State University, who's done a lot of theoretical work as well as a lot of very good applications work using approximate techniques, approximations to the synchrotron equations. And that's what he's going to talk about this morning, is some of the comparisons and meanings of more simplified approaches to unsteady flow modeling.
Thank you, Mike. Good morning. First, I would like to thank Mike G. and the Hydrologic Engineering Center for inviting me to share with you some of my experiences in unsteady flow in the last 10, 15 years that I've been working in this area. I am going to take charge of this lecture this morning and an early lecture this afternoon, as well as tomorrow morning, I believe at 8 o'clock. And we are going to go through and cover the material that has been given as part of the workbook, starting where it says approximate models of unsteady flow. Those are the blue sheets. And right behind those blue sheets, there is a set of chapters which contain material that was put together for an unsteady flow course that was taught several years ago at Colorado State University by myself, with Yevgevich and other people. Continuing on the subject that I'm going to be talking about in these 3 lectures, I have included as part of day 3, although I may use some of this material also as part of day 2, I have included a couple of papers that I have put together in the last 5 years that have been published in Hydraulics Division. One of them is titled Accuracy Criteria in Diffusion Routing, which was published in June of '82, and the other one is called Kinematic Shock Sensitivity Analysis, which was published in April of '85. Right after that, there's a set of transparencies on the Muskingum-Kunge method that I'm going to have a chance of discussing in more detail tomorrow morning. In addition to this information, every once in a while, I will give a reference to publications and papers that I have put together in the past that are not necessarily, in fact, they are not included in here. For those of you that want to go ahead and continue in this area and perhaps do more specialized study that what we can do within the format that we have here at, for this course on unsteady flow. I do want to point out to you that what I'm going to be doing is sharing some of my experiences. If you have other experiences, if you feel that some questions that you may have that may help all of us understand better the topic, please feel free to interact with us. If you can raise your question and answer, or question, and so that perhaps I can answer or some other person can answer. If not, what I'm going to do is I'm going to use the last 15 minutes of the lecture so that we can have a question and answer period on this subject. It is, I believe, a very important subject, and Mike G. as well as the staff here at the Hydrologic Engineering Center have identified it so. The reason for it is that simplified models are used in practice, so we cannot neglect them. So we want to know how good they are as compared to the full-blown unsteady flow dynamic wave model such as the WAPR. And it's an important thing, I repeat, because of the fact that the use of simplified models implies the use of a much lesser amount of resources than if we go ahead with the full-blown dynamic wave model that I'm sure you're going to be covering by at the end of this week when Danny Fred covers that material. So, with that introduction, then let's get started here. And I'm basically going to be using let's see, how do we go in here? Uh-oh, there's a problem. Okay. How does that? Uh-oh. Okay. I have titled this lecture, Approximate Models of Unsteady Flow. And I'm going to be covering several topics which I believe are important for us to understand what are the approximate models and how do they fit together with the overall scheme of things. The first thing I'm going to be talking is the Seddon velocity. Now you may not know this concept by Seddon velocity. You may know it by the Seddon law or the kinematic wave celerity or whatever. But it will be apparent after we discuss this subject what it means and how does it fit within the overall framework of unsteady flow. Then we're going to be talking about the Lagrange velocity, and we will compare the Lagrange velocity to the Seddon velocity. Then that would lead us very nicely into the subject of these three waves that we commonly use in unsteady flow analysis. And in fact, we use them not only in theory but also in practice: the kinematic, the dynamic, and inertial waves. And at this point, when we get down there, I'm going to add even one more wave that I think we ought to know and we're going to be discussing tomorrow in more detail. Well, in addition to these three, we're going to be discussing the diffusion wave or zero-inertia waves. Those are the waves that I believe that have a tremendous applicability in the subject of flood routing, which I'm sure we're all interested in. Then we will compare the steady versus unsteady flow rating curve so as to throw some light into the intricacies of doing this calculation. And what is it exactly that we're doing when we calculate unsteady flow? Boundary conditions is another important subject. I'm sure through the remainder of this week you will hear lecturers come in and talk about what are the various boundary conditions that ought to be covered or ought to be dealt with when dealing with unsteady flow. And finally, and this is the subject in which I believe, as Mike said before, that I have contributed directly in the subject of unsteady flow, and it is how applicable are these models, these approximate models. How good are they in terms of their use for everyday practice? And I believe that we will be able to answer that question in a straightforward fashion. First, we should define unsteady flow, and of course this is our second day of the week, so I don't think I should spend too much time doing that. Unsteady flow, as you know, entails the variation, the calculation of the time-wise or temporal variation of discharge and stage. Discharge and stage. Discharge we're going to represent by a Q, stage Y. So the variations in time of discharge and stage lead us to the calculation of unsteady flows. Now this could be done in two ways. One could simultaneously calculate these two variables using two equations. And in that way it becomes a hydraulic calculation. By using two equations in two unknowns and a simultaneous calculation, and it becomes a hydraulic calculation. And this is what precisely models such as DWOPR as well as other unsteady flow models would do. On the other hand, you can choose the simplified route, which is to calculate the discharge first and then use that discharge on which to base your calculation of the stage. And in that sense, it is simplified, obviously, because it implies the uniqueness of a rating. And in that case, then we say that that approach is hydrologic. And such an approach would be one that would be used, for instance, such as in the hydrologic models in current use. For instance, HIC1, TR20, as well as others. They will calculate the discharge first, and then use that discharge, and through a rating, calculate the Y. So the main thrust of our analysis here, as well as this afternoon, would be to determine what is the difference between these two approaches. When can we afford to go the hydrologic way? And when are we getting out of the limits in which we could do this calculation in a hydrologic fashion, and we have to go perhaps to a more elaborate model that will give us simultaneous calculation of discharge and stage? In order to do that, we have to understand some basic concepts. And these concepts have been around for a number of years. I can recall going back to the paper by Lytle and Whittam that I'm sure some of you have read. It's a highly theoretical paper. It's a hard paper to read. But the paper by Lytle and Whittam in a British journal in 1955 gave publicity, if you wish, because I don't believe that they actually developed this concept, but they are widely recognized as being a paper in which this concept acquired popularity. And this is the concept of the kinematic wave velocity, the kinematic wave, as opposed to a dynamic wave. Implicit in the concept of the kinematic wave was that the wave had to be big, massive. In fact, Lytle and Whittam titled their paper, they titled it Flood Movement in Long Rivers. And I believe by long they implied that the wave was long, not necessarily the river. Because what is a long river? I mean, you know, you have to figure out what exactly is it that they're talking about. They were talking about, I believe, about a wave that was long, that was very massive. And therefore, they developed their theory of kinematic waves based on this concept of long waves as opposed to short waves, which we'll have a chance to talk about later on. Cho, when he wrote his book, Venti Cho, in 1959, Open Channel Hydraulics, which I'm sure all of you have reviewed and studied and worked with it. A very good book. In the last 3 chapters, he talks about unsteady flow. And in there, he says, we're going to talk about the monoclinal wave velocity. And he presents this derivation that I'm presenting here to you. Do we have a pointer, Mike, or should I just?
One resting against that chalkboard.
Okay. And he said, if we have a wave that is monoclinal, that is just a wave that it's rising, it is not receding, okay? And he went about this calculation, which showed in a rather straightforward manner that there was a velocity to that wave, different from that of the flow. And then he called that velocity the celerity, to distinguish it. To distinguish the fact that what we're talking about here is the velocity of the surface as opposed to the velocity of the mean flow itself. So he said, if I take this velocity, c sub w, say the celerity of the wave, and we multiply that just by strictly applying a principle of mass conservation, and we multiply that times the difference in areas, A1 minus A2, or rather A2 minus A1, in this case it's actually A1 minus A2. This is somehow of a mistake here. That would give us, that should be A1 minus A2 because A1 is the upstream. That would give us A2 V2 minus A1 V1. That would be the difference in discharge, okay? Actually, in this case, it turns around that because I took the signs in a negative way, it ends up being positive because A2 V2 is Q2 and A1 V1 is Q1, and therefore you have a positive value for the celerity. Okay, so what does this mean in practice? It means that the change in discharge with respect to the flow area gives you a velocity, and gives you a velocity of the face of this wave based on just strictly using mass conservation principles. However, I don't believe that Cho at the time told the whole story. And the whole story is the fact that if this wave had receded back in here to this point, it is likely that in the mean, the receding in the mean, and let me qualify that later by what I'm going to say, that the monoclinal velocity would be pretty much equal, the rising limb would be pretty much equal to the receding limb in the mean. And that therefore, we have in here a kinematic wave. And in fact, when Cho talked about the monoclinal wave, he was actually referring to this velocity which is earlier by Lighthill and Whittam and later by several other people, has been identified as being the celerity of the so-called kinematic wave. We will have a chance to talk about later on, when I talk about the kinematic shock, as to how locally these individual parts of the wave can differ from each other in terms of the velocity or the relative celerity that they have. But we'll talk about that later. Okay, so we have this Seddon velocity, or the velocity of a very large wave compared to the channel. In practice, the change in discharge with respect to the flow area is something that theoretically appealing, but it's not a very good practical term. So what has been done in practice is that we have been able to talk about the flow, say the cross-section, the stage Y, and the top width of the channel, and the change in area is going to be equal to the top width times the change in stage. And that is a well-recognized formula in open channel hydraulics. Therefore, we can say that the celerity, or the velocity of this wave, if you wish monoclinal wave to follow Charles' notation, or kinematic wave to follow Lighthill and Whittam, would be equal to the Q over dA, where dA now is the top width times the change in stage. So all you need to do in order to determine this velocity is to have a rating curve, and obviously this curve has to be a mean rating, an equilibrium rating, a steady flow, so to speak, rating. Because otherwise, for each rating, you'll have a different velocity. And in fact, this is what makes the problem more complex later on. So if you can pose to yourself an equilibrium rating, such as is used in hydrology when you want to change, when you want to convert from discharge to stage, then you can say that for a certain discharge, you have a certain stage, and you have a slope of the rating. And that for that same condition, you can have a geometric function that describes the stage with the top width, the variation of stage with top width. So you can get the top width out of here, out of these two functions, and with the top width, then you can plug that back in here, and you have the change in discharge with respect to stage, and lo and behold, you will get the Seddon velocity, or the velocity based on Seddon's law. I'm sure you realize, or you know, that the reason why this velocity is called the Seddon velocity is because it is based on the paper that was written in the year 1900 by Seddon in the Transactions of ASCE. Seddon did a tremendous amount of work in the lower Mississippi, as well as several other rivers, and concluded after many years of study that his data followed this law. He said, this is the law, and I read that paper. I don't know how many of you had a chance to go that far. You know, we're talking 1900. You know, he said, this is the law that the river will conform. And he put it in there. And ever since then, that law has been called the Seddon law, or the Seddon velocity. If you go to Europe, you'll find that in Europe they call it something differently, because in Europe they had somebody else that did that work somewhat earlier than Seddon did, so they call it the Clyde's law. So whether you call it the Clyde's law or the Seddon law, it is still the same concept. It is the speed of perturbations, which are massive, they're large perturbations, and that are unsteady flow per se. This concept of the Seddon law can be expressed in many ways. Just the ones I've given you are just two ways. There is even a third way in which this concept can be expressed. One could take for purposes of simplifying the formula when you don't have a rating. This is one instance in which it could be used this way. If you don't have a rating and somehow you got the hold of the Manning's formula, it can be simplified. You can express the Seddon velocity in an alternate way. And this would be by simply saying that the velocity of the flow in terms of Manning's formula, as you know, is equal to 1.486 over the Manning roughness constant times the hydraulic radius to the 2/3 power times the slope of the friction or friction slope to the 1/2 power. And therefore, if we want to calculate the discharge would be equal to the V, the velocity, times the area. That means we have to include an area in here in addition to the velocity. And therefore, since the hydraulic radius is by definition equal to area over wetted perimeter, then we can say that the area in here to the 5/3 and the wetted perimeter to the 2/3, and then we can, and here we're following something that Light and Whittam as well as Seddon and many other people have done in order to make it solvable and that could be applied in practice. For the time being, we assume that P, the wetted perimeter, the slope, and the Manning's N are constants, and therefore you can get up a rating that looks like this. Everything else other than A is constant, independent of A or Q for that matter, and then you get a rating that looks like this. Alpha is equal to 1.486 over N, S of F to the 1/2, wetted perimeter to the 2/3 power, and beta, now here beta is equal to 5/3. Of course, beta is equal to 5/3 under this derivation, based on what we have assumed, which basically is two things. We have assumed that the wetted perimeter is a constant, and we have assumed that that we can pose the friction in terms of the Manning equation. We could choose some other equation, but we use a Manning because that's the one that's used by most people in practice. So that means that this beta is applicable under the conditions of a wide channel, a very wide channel, because a wide channel, we can assume that the wetted perimeter is a constant, as an approximation. So for wide channels, theoretically infinitely long or wide channels, and of course that doesn't happen, but you had a very wide channel of depth to width of 100, or even anything more than 10 or 15 would be considered to be a reasonably wide channel. This beta then is 5/3. Turbulent Manning flow under wide channel assumption. Now if you take the Q dA, the derivative of Q with respect to A, assuming of course alpha and beta to be constants for the time being, we would get this alpha beta to the A beta minus 1, right, taking the derivative, and because we have in here beta Q to the, in order to put a Q in here in the denominator, we would have to have an A, in the numerator, we would have to have an A in the denominator, and that leads us to this formula, which says beta times Q over A, and since we know that Q over A is the mean velocity, we come to the conclusion, which is supported by theory, supported by experiments, supported by just about everybody, that the kinematic wave velocity exceeds the velocity of the flow, typically by 5/3. In this case, of constant wetted perimeter under Manning's law, by 5/3 is 1.67. This beta coefficient of the rating, or exponent of the rating, has a way of changing. As I say in there, it's for Manning friction in wide channel, where P is a constant, beta would be 5/3. However, in practice, this beta coefficient may vary, and in fact, it does vary. If you pose a Chesi formula instead of Manning, which you could if you wanted to get into theory, Chesi formula is sometimes more theoretically appealing than the Manning formula, then that beta will turn out to be 1.5 instead of 5/3. If you pose a condition of a triangular channel, not a rectangular, but a triangular channel, then the beta reduces to 4/3 instead of 5/3 for Manning's N, and to 5/4 instead of 3/2 for Chesi. And in fact, if you were able to pose a situation in which the width, that is the wetted perimeter of the channel, expands at the same rate as the area, and admittedly you would have to really get a very weird channel in order for that to happen. It would have to be something like this. And I have plotted this, by the way. There's a function that describes this channel. If you were able to get a channel that looks, well, you know, take my word for it, more or less like this, well, it has to be increasing though. It has to be going like that, in such that the wetted perimeter will increase at the same rate as the area, then you'll have a beta equal to 1. that means the beta, that means that the velocity of the wave is going to be basically the same as the velocity of the flow. At that point, they're going to be matched. But that is a very unlikely condition unless you go into some kind of overflow, overbank situation, which obviously, even in the overflow situation, you may not get quite there. So the beta for practical purposes may range anywhere from 1.7 to 1.5 to 1.3, very seldom getting to be a value of 1. This is unsteady flow. It's a description of, it's a parameter that describes the actual speed of this wave, this kinematic wave, this Seddon wave. So it is an important concept that we should really understand. So this is a third way of doing it. Normally, out of these three ways, the one that is more practical would be the second one, dq over the width over the dy. That would be the second, the one that would be for more practical applications, the one to use. The other two are also useful when you're working with models. Sometimes it is necessary, in all of those of you that have worked with models, it is necessary to cut some corners because it gets very complex. The problem really quickly gets very complex. So if it's necessary, then we can use this other equation that the one where it says that the velocity is equal to beta times v. So this is then the concept of the Seddon velocity, and I repeat, that is the kinematic wave. The kinematic wave is a well-established concept. It is used in HEC 1. It is used in many hydrologic computer models. It is, in fact, it is the preferred method currently for hydrologic computer models, not for hydraulic models. See, so we go back what we say in here. For hydrologic computer models, the kinematic wave and so on and simplified waves are currently the preferred method because we believe, at least the people that have developed these models, that going full-blown with the full equation is a rather complex subject at this point. And for network models, it has not been implemented. Well, it has, but to a limited extent. Because I know Danny Fritz is going to come here in a couple of days and going to say that it has been. Okay? But we'll talk about that a little bit more later. For one thing, HEC 1 hasn't done it. You know, and I'm sure a lot of you are going to be using HEC 1 later, and that's going to have to be the case. Okay, we shift gears for the moment here and leave the kinematic wave velocity and leave the concept of the very, very massive, large-scale waves in unsteady flow in open channels. And now let's go back to the laboratory. And let's go back to Cho, or many other books that have been written on the subject. In fact, in chapter 18 of Cho, he says, there is also waves and celerities that can be calculated. Among them, several formulas for waves, for celerities of waves that he mentions. And he makes emphasis or emphasizes a certain wave, which is called the Lagrange Velocity, which I'm sure all of you have come across in the past. This velocity, or the celerity, was developed in a paper written by Lagrange, I believe about a couple of hundred years ago, if I'm not mistaken, in France. Lagrange wrote a paper, and he said that the waves tend to follow, and he didn't quite actually dwell into the specific nature of these waves, but he says the waves I've measured tend to follow this formula, the square root of g times y. Of course, provided that they are small amplitude waves. If you have a wave that has a finite amplitude, then that can be corrected for amplitude effects. But in general, this formula here is recognized as being the typical or classical formula, if you wish, for the travel of perturbations. But these perturbations are the small perturbations, the ones that are seen in the laboratory flume, not the ones that you see out there in the field, not the ones you really have to deal with from a flood standpoint, because none of these perturbations are going to cause a flood, because they're too small. Okay? The very small waves. And these waves, as we will later see, are governed by pressure gradient and inertia. And we'll have a chance to get to that later on. There's a fundamental difference, other than the fact that there is a scale difference between this wave and the Lagrange wave. I'm sorry, between the Lagrange wave and the Seddon wave. There's a fundamental difference. And the fundamental difference lies in the fact that this wave is generally expressed in terms of this. Look at that, plus minus. It's a two-component wave. It means that there is a perturbation somehow caused in a river, that perturbation, based on a one-dimensional, frictionless approach, and we'll get to that later a little bit more, it will travel upstream and downstream. It will have the velocity of the flow, if you have a flow velocity, and it will be v plus minus the square root of gy. If the velocity is 0, if the flow is at rest, of course it will be plus minus gy. But otherwise, if there is a velocity, then this is what's going to be. And again, I repeat, the fundamental difference, other than scale, between these two formulations for unsteady flow are this one has two solutions. It corresponds, in fact, to a second-order equation, because a second-order equation has two solutions. On the other hand, the Seddon wave is a first-order equation, and it has one solution only. We cannot get a solution out of the mathematics. And in fact, that shows that I guess in our practice, it tells us what we already know, and that it is that mass waves, or massive waves, namely flood waves, do not travel upstream. Right? They travel only downstream, as opposed to this wave, which will travel out upstream. But let's leave for the moment the concept of them being basically mathematically different, but rather the fact that in practice they're also different. Because it is the Seddon waves, the ones that we're most interested in calculating and depicting and knowing how is it that they behave. We're really not too much interested in Lagrange waves, unless, of course, you're in the tidal environment, in which case both of them get together. But if you're in the inland river environment, it is likely that you would have a lot more to do with the Seddon wave than with the Lagrange wave. Unfortunately, for reasons that I don't know quite how that has happened, the Lagrange wave seems to be very popular, while the Seddon wave not popular. I've seen people, I've lectured, in other places, and they say, we know the Lagrange wave, but this Seddon wave is a new thing to us. Well, it's relatively, of course, Lagrange wave has been around for 200 years, and Seddon only about 80 or 87 years, but certainly these are two very well-established concepts in hydraulics. In hydraulics of flood hydrology, and so on. If I have my pick, I would choose any time. I would choose the Seddon wave, because it is the one I have to deal with on an everyday and a daily basis. Okay? Let's compare these two, Seddon and Lagrange velocities, and see where is it that they match. And if indeed they do match. Okay? So the Seddon velocity is going to be beta times v. And the Lagrange velocity is going to be v, which is the mean velocity of the flow, plus minus square root of gy. In order to compare this velocity, we can only compare the downstream component of the Lagrange velocity, because we already said that there is no flood wave moving downstream. So we're going to take the downstream component of the Lagrange velocity, which is v plus square root of gy. Okay? And let's assume here, for purposes of illustration, in order to make a point which I will later on, that we're shifting from Manning to Chesi here in the way we calculate the beta coefficient. And you can go back and repeat what I did for the Manning equation. And I ended up with a number which was 5/3, right? And you can do the same thing for the Chesi equation, and you're going to get a number that is 3/2. If I do that, then I can say that this is 3/2 and this is beta. 3/2 of beta. And now I'm going to force that to be equal to the downstream component of the Lagrange formula, and see what am I going to get. What am I going to get? I'm going to get 3/2 v minus v. Well, that would be 1/2 v, right? V over square root of g, okay, equal to 1 over 1/2, that is equal to. That means that for a fruit number equal to these two concepts, Lagrange and Seddon, seem to coalesce. They seem to become one. Now let's explore for a moment, what does the literature say about the condition of fruit number being equal to? You can go back to the work of Dressler, the work of Lytle and Whittam, and others that have shown that for fruit number equal 2, there is flow instability on the surface. And in fact, these are the so-called roll waves that Chow, as well as many others, have described, the roll waves. We conclude, based on this, as well as other analysis that I will have a chance to refer to, that for the fruit number equal 2, which most of us like to stay away from, don't they say in the design literature that you ought to stay away even from fruit number equal 1, that you should not approach the fruit number equal 1 because it causes instability, and let alone 1.5, which would be the equivalent in the Manning formulation to this 2 in the Chesi formulation. So we do like to stay away from the design standpoint from these high fruit number flows. However, we do realize from a theoretical standpoint that at fruit number 2 in the case of Chesi and fruit number equal 1.5 in the case of Manning, we have a situation where the surface of the water, the water surface becomes unstable. At that point, its own mechanics acts in such a way as to amplify disturbances. So any disturbance that is created by whatever means, and you know there are many possibilities for creating disturbances, boundary conditions, and so on, these disturbances will be amplified to the point where they look so uniform, and they are like jumps in the channel. They look like this. And these are the so-called roll waves, as well as which typically depict the onset of instability. At that point, of course, the problem that we have with the roll waves is that the way the water is trying to jump around all over the place, and then pretty soon we lose the mathematics. The physics lose the mathematics. You can agree with me that if the water is going to jump in here all over the place, then we're not going to have constant flow anymore, and then our theories stop the work. However, we do learn from the hydrodynamic analysis that we have in here a fruit number equal to where these two are the same. In fact, we can show to ourselves that if we had this condition, and that, by the way, is fruit number equal to is Chesi friction in wide channels. 1.5 would be Manning friction in wide channels. So you got to have, in order to determine this onset, this threshold of fruit number or free surface instability, you would have to not only determine what the friction is going to be, whether Manning, Chesi, or any other, well actually there's only two, but also the cross-section. What is the cross-section going to be like? If you have a rectangular channel, wide channel, then it's going to be that. But if the channel looks like this, then it is going to vary. And we can show it to ourselves, and I've done it, and we'll talk about this when we get there, that if you have a channel like this in which the wetted perimeter increases at the same rate as the area, the fruit number for instability is equal to infinity. It's an infinite value. So you cannot, under any circumstance, have instability with such a cross-section, because it's just not going to be there. The hydrodynamics tells us it's not going to be there. And that is obviously the reason why you don't have roll waves in flows that cover the floodplain. You know, you may have little, the more coverage there is, there's a less the chance of producing these very well-defined roll waves. Notice that if we apply a typical fruit number, say fruit number equal 0.1, if we're going to do a calculation with a typical fruit number, and I'm sort of exaggerating the value here to make a point. I could have used 0.2, but that wasn't going to make that much of a point in there. So I use 0.1. If I use 0.1 in here, this says that 1 over 0.1 is 10. That means that the downstream component is going to be 11 times the velocity, and the upstream component, it's going to be minus 9 times the velocity. That has been erased, but I believe you have it right. You have it right in your notes. Minus 9 times the velocity. So we conclude that generally, for the fruit numbers that we care to deal with in practice, that the Lagrange velocity, which is the velocity of the small waves, is much greater than the Seddon velocity. And it is also dependent on the fruit number, while the Seddon velocity is independent, at least in this type of formulation, of the fruit number. Now we have seen two concepts very well established. One of them for the large massive waves, another one for the very short waves. And in fact, I am now going to say that the size, you can feel the effect of size and scale. We all can do that. But we are less able to recognize the fact that the Seddon concept or the Seddon criterion is a statement of the transport of unsteady transport of mass. On the other hand, the Lagrange criterion is a statement of the unsteady transport of energy. And they are the entirely opposite sides of a coin. That on the one hand, when you deal with flood waves, you're talking about Seddon law and you're transporting mass. Everybody will agree with me that the water's got to be going downstream, right? It's moving downstream. It's not staying up there. On the other hand, when you talk about Lagrange waves, the water's not going anywhere. It's just rotating around itself. And it is the energy that is being transported. And these are two fundamental concepts. So we can go back to the mechanics, we can go back to, if you wish, to basic mechanics principles. But that is the fundamental difference between these two concepts. On the one hand, mass transport. On the other hand, energy transport. At this point, you may say, oh, so that means that we can combine these two and transport mass as well as energy. And I say, well, be my guest. You know, because it's a tough job to do, but we'll see how it is done. Okay? Okay, so we then, by looking at the theory, we have to acknowledge that there is four major forces in this unsteady flow framework. And that is, these forces are going to be the forces of gravity, the force of friction, the force of pressure or the pressure gradient, and the force of inertia. And let me restate in here what I mean by that, and I'm sure that all of you would agree with me. You have a control volume, or other people call it just a stretch of channel, a channel reach. And you're going to have the force of gravity. Here you have the weight and the gravitational force resolved in the direction of motion. And you're going to have the integration of the force of friction along the bottom, which is given by the Manning's N. It's represented in the Manning's N. For the general condition, you're not going to have the two water surface slope and bottom slope parallel, so you're going to have a situation like this, exaggerating this, and you're going to have a pressure in here which is different than the pressure in there. And we assume, of course, for gradually varied unsteady flow, that the pressure distribution is going to be hydrostatic. For most cases, we can get by with it. So, since these pressures are different because of the fact that the depths of flow are different, because there is a depth of flow difference, then there's a pressure difference. A pressure difference leads to the pressure gradient, which leads to a force. If there is an imbalance between these three forces, let's say the force of pressure, the force of gravity, and the force of friction, you can resolve these three forces along a certain direction of movement. Normally it is the direction of flow. Somehow we can define the direction of flow. If there is an imbalance between the three forces, then immediately another force pops up, and that's Newton's force, right? The inertia. So inertia, I can't picture it in there. I'm going to put it in here. But the inertia has two components. It has a local component by virtue of the inertia itself, and it has a convective component because of the fact that we are very conveniently choosing to stand and let the flow go by. To stand in a certain place and the flow is going by, and that's the way that's called the Eulerian presentation. If we, on the other hand, were traveling with the flow, then there would be no convective inertia, and we just had local inertia to contend with. But since we conveniently, at least in the first type of introduction to the subject, we choose to stand in a certain place and let the flow move by, then we have the convective inertia. But these two forces together, local and convective, are called the inertia force. And in a Lagrangian formulation, which perhaps you're gonna cover a little bit of that, then you will get rid of this convective inertia and just cover the local inertia, and well, so much the better. Whatever. So you have these four forces that you have to contend with, you got to solve. Well, it so happens that Seddon law is based only on two forces, only in friction and gravity. That's Seddon's law. That's a statement of Seddon's law. So you may say, well, what about the other two? Well, Seddon says they don't matter. As far as my data has been shown, I have proven to myself that it does not, they don't affect my calculations. You may say, well, wait a second, well, these two forces look like they're important. Well, you can go back to the paper by Seddon, you can go back to kinematic wave theory and so on and so forth. As far as that, they don't matter. Now, if on the other hand you took the opposite side of the coin, you said, well, let me pose a condition in which the gravity and the friction don't matter. That would be kind of hard, wouldn't it? But I can tell you easily, I can tell you that the gravity is not going to matter if the channel bottom is flat. Right? There's not going to be a driving force in the direction of the motion. The component is going to be zero. The friction don't matter. Well, you can say we can now play God, right? Friction is there, out there. But if the reach is very short, the friction is going to be also very small compared to the disturbance. The disturbance is going to be big. The friction is going to be small. The gravity is going to be non-existent. Therefore, that's Lagrange's formulation. We here compared the pressure gradient, and I've exaggerated this, the pressure gradient and the inertia. He says, okay, we got the pressure difference, and this is the only force. Since I cannot build an equation with one force, that would be ridiculous, it would be trivial, I have to put in there another force. That's the force of inertia. I balance these two, and we get the Lagrange velocity. Okay? It follows then that we conceivably, and I put a quote unquote in here, conceivably improve on what Seddon did, improve on what Lagrange did by putting all this together, all the four, in transporting mass at the same amount or the same time as we transport energy, solve the whole problem once and for all. And in fact, this is why you fellows are here, to solve, to learn how to do this, to go over and above, beyond what the Lagrange formula can give us, and even more what the Seddon formula can give us. So we're going to combine these four forces, and no matter how important they are in relation to each other, we're going to put them together into a model that we call the dynamic wave. That is what, in most hydraulic books and references, it's called the dynamic wave, as opposed to the kinematic wave of Seddon. And here I'm going to take exception. I call it inertial wave. In most books you will see this as referred to as gravity wave. I don't like the word gravity wave, because I was saying in here that I'm taking gravity out of it. How could I call it gravity wave? To me it's more like a balance between inertia and pressure. And in fact the Dutch had realized this many years ago and had started calling it inertial wave. And I followed on their tracks. There's a couple of publications by I can't recall the name right now, out of Delft. But they call this wave the inertial wave, but to give it the right name, that we believe it should be emphasis on the inertia rather than the gravity, which is non-existent in there. So we have in here the inertial wave, pressure and inertia, the kinematic wave, gravity and friction, and the dynamic wave, gravity, friction, pressure, and inertia. Now we have complicated the thing, right? Now we not only have two, we have three. Well, let me tell you that there's also a fourth one out there, somewhere. And I'm sure a lot of people could also talk about fifth and sixth and seventh. I'm not going to get into that. That would be complicating things too much. But there is another wave in there, which is a fourth type of doing these things, which I'm going to have a chance to talk about tomorrow. And that's called the diffusion of zero inertia wave. In this diffusion wave, we say, let's take gravity, friction, pressure, and forget the inertia. Zero inertia. And that leads to the diffusion wave. Okay? In fact, however, the diffusion wave, the subject of diffusion wave is very is a very fluid subject at this time. That was not intended as a pun. It's a pun. It's a fluid subject at this time because there is indications that the diffusion wave, or what looks like a diffusion wave, could also be construed or comprise, could also comprise the inertia. So you can have a diffusion wave with inertia too. And therefore there's a confusion as to what is what. Okay, but there is a confusion in the literature as to this, but we'll have a chance later on. We'll review this in more detail. So in river flow, gravity and friction are always there. You have gravity and friction. Why? Because in inland river flow, we always have a slope, no matter how small it is, but it's a slope, right? You can say in the mountain rivers, I'm going to have a slope of as great as about, I believe you would agree with me, 6% is about as great as it is going to get. Very seldom does it go above that. In the tidal environment, you're going to get very small slopes. In fact, I've been researching this particular subject as to how small you could get short of zero. Zero. And I have seen Danny Fred, for instance, in his recent paper. In fact, I believe that paper is part of the collection that you have in there. And he has put 5 zeros in here, 506. If your experience tells you something different, please let us know. On that order, okay, very small slopes. You can vary the slope widely, but it's not zero. If it were zero, then technically you could not pose a Seddon condition. But because it is not zero, then we're able to say, well, the Seddon law applies. That is why when Seddon did his work in the early 1900s, he was working in the lower Mississippi. He wasn't working up there in the high mountain streams. No, he was working in the lower Mississippi. And the reason why, when we talk about applicability, we will find out the reason why is that Seddon's law did work, even though he was working in the very low slope streams such as the lower Mississippi. Under certain conditions, inertia and pressure could be small, and here I stress could. And here there are several philosophies with regards to this subject. How small is small, or how big is big? You know, it's hard to define. Everything is relative, right? So if anything you say this term is small, you have to say small with regards to what? You cannot say it's just small, right? So when I say in here small, I have to say with regards to the other two. Inertia and pressure could be small with regards to the other two. Obviously the 4 are in there. But if they're small with regards to the other two, then they could be neglected. And that leads to the Seddon law. This subject has been thrown around in the literature for many, many times. It started with the work of Hayami. I'm sure you will recognize the name. In 1951 in a Japanese journal. It continued with the work of Lytle and Whittam in 1955 in Britain. Wooding picked it up in 1965, writing in the journal Hydrology. It was pursued later by Wilheiser and Liggett in 1967 in the Water Resources Research. And this led to the kinematic wave equation. Okay? And so in the use of the kinematic wave as a predictor or a valid model for flood waves. Let's look at this problem from a practical standpoint. I think that at this point Mike asked me to be very practical, and sometimes I have a way of getting into theory because of the fact that I've done a lot of work in this area. But let's go back into the practical. What can we say about, let's take a wave. Let's talk about a flood wave that we would like to deal with. Let's say characteristics, 30 foot high. That's not bad. It's a good number, I feel. 30 foot high flood wave. 24 hours time base. Now the time base, for those of you that are not in the hydrology, the time base is a hard thing to pin down. Many people can talk about time of rise, but very few can talk about time base. But I have to in here because I'm going to make a mathematical comparison. You have a flood wave, okay, and the time of rise is very well defined. But the time base is not very well defined because of the recession and the fact that we very seldom can accurately pinpoint exactly where is it that the recession is going to finish. But for practical purposes, we could say if it comes back within, say, 1% of what it was before, in here, I can say that this is going to be the time base. I have done theoretical work with sinusoidal waves because of the fact that you can use, in theory, sinusoidal waves in very easy fashion. You have all the backup of analytical calculus, or calculus rather, to do work with sinusoidal waves. But sinusoidal waves, you would agree with me that very seldom do happen. A sinusoidal wave goes like this and it comes back. However, it is somewhat of an indicator as to the shape of a flood wave. In reality, the flood wave tends more to be a collection of sinusoidal waves, and in actuality, the shape may look like that, with a receding limb having a somewhat different of it's a much flattened way in which it recedes. But let's assume for the moment that we can talk about a time base of a certain flood. And let's say it is going to be 24 hours. Not unreasonable. It's a small watershed, though. It couldn't be too big. I would say, those of you that work with the lower Mississippi, when the flood goes up, and if it takes, what, a couple months to come down? Right? In fact, I was doing, a few years back, I was doing work in the Alto Paraguay. That is a very huge basin down in the boundary between Brazil and Paraguay. And the time base of that, of the outlet of that basin is 1 year. Exactly 1 year. And that, I believe, it has to be one of the very unique cases in the world where that happens. Let me show you what the hydrograph at the outlet looks like. It's a huge basin, I believe something on the order of 600,000-700,000 square miles. I could be wrong on this one because it's been a number of years. But the outflow looks like this, where the peak is somewhere in the end of May, beginning of June. So the time base for this, in fact, this one turns out to be almost sinusoidal. It has to be, more or less. You know, it's not that steepened because it underwent a whole lot of diffusion because of the fact that it's a huge basin and it's very flat, and therefore it produces a hydrograph that looks like that. They already know when it's going to, more or less when it's going to peak. The only thing they have to do there is to use the hydrologic model, such as SAR. In fact, they use SAR in order to predict how much flooding they're going to have. They know they're going to have flooding for sure, unless they run into dry years in which they're very, very low, and you know the dry years happen to be together with the dry years and so on and so forth. Whatever, but that's the concept of time base. So let's say we have a velocity of wave velocity of 10 feet per second. That is not unreasonable either. That would be typical of somewhat of a fast-moving stream, 10 feet per second. If that is the case, then we can say that the length, okay, because the celerity is equal to the length over the time. When you talk about sinusoidal waves, this is, in fact, a formula that could be used. The celerity is the length over the time. And therefore, the length of this wave, quote unquote, right, it's going to be celerity times the time. If the celerity is 10 feet per second and the time is 24 hours, 86,400 seconds, then we would get 864,000 feet, which is 164 miles. This to show us that when we're dealing with flood waves, we're dealing with very long waves. This is not the longest. By any chance, by any stretch of the imagination, it will be the longest. We could have said in there 30 days time base, and so on and so forth. Okay, they're very long waves. And in fact, they're waves just because we choose to call them waves, because they look like waves if we portray them in a blackboard like I do. I could say in here, this wave here is 30 feet, right? 30 feet in here, and 100, and what did I say in there? 864,000 feet in here. And you would agree with me that I have highly distorted this wave. I mean, I have almost, you know, totally compressed this wave so that I could write it. I could put it in there like that. Now, these are very common sense terms. I mean, I may not be saying anything you don't know already. But the fact of the matter is that these waves are massive and they're very mild. If I had to draw it to true scale, I couldn't do it. Simply as that. I positively could not do it. I have to do it in distorted scale. 30 waves and 800. So these are the waves that are transporting mass. Therefore, here's where the concept of the Seddon law has being then, or comes into being. And it is that in this case, because of the fact that we have such a massive wave, the pressure gradient and the inertia may indeed be negligible as compared to gravity and friction. Because the inertia term is 1 over g du dt. That's the inertia term in most simplest form, in its most simplest form. And du dt, you would agree with me that u doesn't vary too much. Let's say, well, I'm using u in here when I should have used v. Let's use v. Let's be consistent here. V is the mean velocity of the flow. You would agree with me it cannot vary too much. It could vary from 3 feet per second to about 12, 15, perhaps 18 feet per second. It varies within less than 1 order of magnitude. But because we're taking the rate of change with respect to time, and since this is such a slow-moving wave, then this becomes a very small term. And if furthermore you divide that by 32.2, then it becomes even further, much smaller than everything else that we could care to put in there. This concept has been documented by Henderson in his book in 1965. It has been documented by Strelkov here as part of our workbook in 1980 in some work that Strelkov did for the Hydrologic Engineering Center. It has been documented in 1978 by myself, as well as many other people that have dealt with approximate models. And they have come to the conclusion that the terms in here, that these two terms, the pressure gradient and the inertia, may be negligible. If they are negligible, if indeed these two terms can be neglected, and we'll have to apply some quantitative measure of neglect. In other words, if we're going to neglect these things, we're going to make sure that they're small. And when I mean small, I don't really should say small. I should say they do not influence the solution. That's a better, more engineering way of doing it. Because if your calculation by neglecting them is going to show that your depth is 12.5, and your calculation including them is going to show that your depth is 12.51, then there is where you get your measure of neglect, whether it's good to neglect it or not. Because you can always look at it from the other standpoint. You can say, well, what if, I have the best tool? Why should I use approximate methods? The answer to that question, I've said it in the past, is would you kill a bird with a cannon? It's up to you to do it. Of course, it's somewhat of a coarse analogy, because in here you do get an answer. In the case of a cannon, you don't get a bird. So it's coarse. Okay? So it's the best thing I come up with in order to defend this approach. Okay? So then this would be a kinematic wave. Seddon law could be applicable. It could be a kinematic wave. How are we doing with regards to time, Mike? We have 5 more minutes, right? Yeah, fine. It could be a kinematic wave. So if it could be a kinematic wave, and let me first say that since we are going to be pretty much leaving aside the concept of inertial wave, because we already said that it does not apply for our flood calculations, and we're mostly interested in floods. I don't know, perhaps some of you may be interested in the short waves. In fact, a lot of short wave calculations and theory has come out recently out of Delft and Danish hydraulics. They're having already through with the flood a long time ago, and they're now looking at the short wave. And first, and I say with this tongue-in-cheek, first they use the dynamic wave model to calculate everything, and apparently they ran into troubles with the short waves. So now they're developing models for short waves. So it appears that the dynamic wave model is not the solution for every problem. And of course, there are advanced users such as Danish Hydraulic, Abbott Group, and so on, have now gone into the development of short wave models, namely models that will simulate the Lagrange movement and associated phenomena as opposed to the Seddon movement. But I believe, I think you will agree with me that we are mostly interested in flood calculations, we meaning civils, okay, civil engineers, mostly interested. I'm hoping that all of you are civil. Pardon me if you know, but we're civil interested in floods, so therefore we stick with the concept of kinematic, diffusion, and dynamic. wave. Out of these three, the kinematic wave is the coarsest. You cannot go coarser than the kinematic wave short of going to steady flow. And I'm going to have a chance to talk about that later on, the comparison between HEC 2 and HEC 1, and I know you already are familiar with that subject. I don't know whether I should stress that or not. But we'll talk about kinematic wave as the beginning of the analysis. If you really want to get into the analysis and understand what is this the kinematic wave does and how does it compare with the dynamic wave and how does it compare with the diffusion wave, which is exactly in the middle between these two. You can go from the kinematic to the diffusion, and then the next step, the ultimate step, if you wish, would be to go to the dynamic wave, which is what you guys are going to be doing this week when Danny Fred lectures on that subject. We start with, well, I think we pretty much exhausted. In fact, I believe I exhausted my time. I wanted to leave some room for questions. Why don't we start this at the beginning of the afternoon and we open it up for questions at this point. We have about 5 minutes, I would say, if you... First questions on the subject and then questions on anything. Well, no, not really. I do realize we do have to go back to theory. Much as I, at the time when I started this, disliked it, believe me. When I was told to go back to theory, I said, is there any other thing I can do? I mean, can I get out of this assignment? I was told, no, you got to go back to it. And I went to it and I did it. So it is a matter, it's a state of mind. It's a frame of mind, really. You got to get over it. It's a hurdle, and that is, you know, what has allowed me as well as several other people to talk about this subject and to get deeply into it and analyze and compare the various solutions, practical solutions that we have at our disposal or available to us for solving unsteady flow problems. Well, if not that, then we'll, yes?
Could you go back to page 4 where you have dq, dA is equal to alpha, beta is to b minus 1, both of them, how you derive the next step from
Okay. We have the rating formula. In its most simplified way or terms would be Q equal alpha A to the beta, where Q and A are our variables and alpha and beta are our parameters which contain frictional and cross-sectional information. So the friction and the cross-section are implicit and bundled into the alpha and beta. Okay? Because you got the friction, the cross-section, and this we already said that is a wide channel with Manning's N. So now we take the derivative, and we presume for the time being, and this is, I admit, it's a shortcut, but we do it. We take a shortcut and say, assume that alpha and beta are constant, and take the Q dA, and that is alpha times beta times A to the beta minus 1, right? Taking the derivative. And now we find in here, we find alpha A to the beta is Q. But we have a minus 1 in here, A to the minus 1, which is A in the denominator. So we have beta times Q over A. Okay? In order to write in here Q, we have to take A in the denominator, and therefore you have beta QA, and QA is V. Therefore that is the standard way of, I guess you could say a third way of expressing the kinematic wave velocity or the Seddon velocity. Okay, thank you. We'll be back at 12:45. Or should we make it 1, Mike, instead? Because it looks like...